Wait a minute or so, people trickle in. Okay, I think that's all right. I think we can go ahead and get started. And so I'm glad you all made it back in one piece from coffee, safe and sound. So this is going to be a very short session. It has 2 talks in it, and so we have a suitably generic session title, Creating Compact Objects. And we're going to start off where the compact object is a neutron star with Peter Kosetz.
Hello, can you hear me? Perfect. Thank you for the introduction. So I'm Peter. I'm a starting 3rd-year Einstein Fellow at the CFA. And I'll be talking about this very interesting source, Hercules X1, which is an X-ray binary. So we have a neutron star accreting from a regular star. Some of you may remember that at last year's symposium, I already talked about this source, but we have some new exciting observations about it. So I hope it will be worth your while. And so welcome to my 2nd annual Hubble Symposium talk on this same source. So Hercules X1 is an X-ray pulsar. So it's a neutron star that's highly magnetized and is secreting material from a regular star. Because of this magnetic field, the inner accretion flow is disrupted and follows magnetic field lines onto the accretion columns and the magnetic poles of the neutron star. Because this whole structure rotates with a period of about 1.2 seconds, we get pulsations from this source. That's why it's an X-ray pulsar. But the most interesting thing about this source is this cycle that is about 35 days long of high and low X-ray flux states. This has been repeating for the past 50 years and has been studied in great depth. And these variations are not because of the mass accretion rate changing, but instead we have this warp disk that's seen almost edge on and is precessing with a period of 35 days. So there are periods of time where we can see the neutron star, which produces most of the X-rays, and we see a high state. But then there are other periods of time when the warp disk precesses across our line of sight and obscures the neutron star, and we see a low state. So this is a simulation how this might look like for Hercules X1. So almost all of the X-rays are produced very close to the neutron star, but most of the times this emission region is obscured by some part of the warp disk. But then there are these brief periods of time when we can see directly the neutron star when we see a high state like right now. So this is very interesting because it offers us a variable sightline through this accretion flow. Because of this warp disk precession, our sightline goes through different parts of the accretion flow, and specifically through different parts of the disk wind that is being launched from the disk of Hercules X1, and specifically at different heights above the disk. So by sampling over this precession cycle, we can sample the wind at different heights above the disk. This is a very powerful way to study the vertical structure of this disk wind. Disk winds are interesting and important because they have the potential to carry away a significant fraction of the originally infalling material. For Hercules X1, for example, this fraction could be as large as 2/3 of all of the material that's going through the disk. And by carrying all this mass and angular momentum, they can change how much the neutron star is accreting and also the long-term evolution of this X-ray binary. Of course, they also inject energy into the surrounding ISM. So we would like to know how much energy this is, how much mass is going away in the wind. But since they're typically studied with X-ray absorption line spectroscopy, for most systems we only have one line of sight, and so we don't know. We have very limited ways to figure out what is the 3D structure of this wind, and therefore how much total mass is actually leaving the system. But by studying Hercules X1, by sampling it over the precession cycle, this is a neat way to get around this problem. So I've been working on this source for quite a few years, but now we have a new telescope called XRISM, which can see this accretion system in unprecedented detail. Already in my previous year colloquium, I mentioned this new telescope, which was launched in 2023. And just around the time of my talk last year, we were carrying out this observation with XRISM. XRISM is interesting because it is the first telescope to have a working X-ray calorimeter, which offers a resolution of R about 1000, which for optical and infrared, of course, is not much, but for X-rays, it's very much. And this is achieved by measuring energy of each photon, by measuring the temperature of each pixel on this calorimeter that's shown on the bottom right. And to achieve this, you have to cool it down to 50 millikelvin. But when it operates correctly at this very low temperature, it gives us R of more than 1000, which for comparison is 10 times better than what we had before for the best instrument that we had before, but about 30 times better than the most commonly used X-ray CCDs. So you can imagine this jump in quality. So this instrument is outstanding for studying lines, line positions, line widths, line ratios, exactly the kind of stuff that we need for studying disk winds. So we proposed to observe this source, Hercules X1 with XRISM, and we got it approved in the GO1 cycle for a very long observation of 200 kiloseconds. And here's just the first spectrum from this observation. And in red, I'm also showing simultaneous spectrum from XMM Newton, which is the previous generation spectrometer. And you can really see the big jump in quality. And you can see a lot is happening in this spectrum. There are emission lines, there are absorption lines, there are narrow lines, there are broad lines. So let's zoom in a bit more. And here you really see the power of XRISM. We see these narrow emission lines, but I will not focus on those. The most interesting right now are these two absorption lines of highly ionized iron, iron 25 and iron 26, which is this absorption from a blue shifted disk wind. So since we have a lot of signal, we can start splitting this data set into multiple parts and see how the wind is changing as our sightline is going through above the processing disk and sampling the wind at higher and greater and greater heights above the disk. So just doing a very simple split, we observe 3 different orbits of Hercules X1 in this one long exposure and splitting the spectrum into 3 parts and focusing just on the strongest line of iron 26. We can see that the line is significantly changing as our sightline is going higher and higher up the flow. So the optical depth of the line is getting weaker. The line broadens over time, and it also shifts to the right. So we can see the Doppler shift is increasing. And so the wind is getting weaker, the velocity width is getting higher, and the wind outflow velocity increases as we're sampling to greater heights above the disk. So doing this more quantitatively and doing a more involved time-resolved extraction, we can actually start sampling what is this wind doing in more detail. So with previous spectrometers, we could measure that the wind has a velocity of a few hundred kilometers per second. But with the precision of XRISM, we can see this very precisely, and actually we start seeing the orbital motion of Hercules X1 around the secondary star, here in the red points. Of course, the wind is being launched from the disk, which orbits the neutron star, and the neutron star is in orbital motion with the secondary star. And so we can see these sinusoidal variations in the wind velocity over the orbital cycle. But even if we account for this motion, and just say, like, this is not very impressive for like optical or IR studies, but for X-rays, this is the first time we can really do this kind of study. But even after accounting for this motion, we can see that the wind is systematically getting faster and faster as our sightline samples greater and greater heights above the disk. And velocity is one of the quantities that we can sample with this study, but others are line optical depths. These are shown in the left plot for iron 25 and 26. And on the right, I'm showing, again, the velocity, and on the bottom is the velocity width. So what we see is that this wind is really strongly evolving with increasing precession phase. So as the sightline is sampling greater and greater heights above the disk. The wind is getting weaker and is getting faster as it rises above the disk and follows the streamlines. So this, especially the increase in wind velocity is very interesting because it suggests that either the wind is still in the acceleration phase, which means something about its launching mechanism, or at least the streamline is projecting more and more along our line of sight, leading to this increase in velocity. And additionally, we also see these jumps in some of the points that seem to occur only after each eclipse. So this is seems to be a new component of the wind that was not detected previously. Maybe some kind of wake that's following the secondary star, and it's only revealed in absorption when the neutron star comes out from obscuration by the secondary star. So the next and the future step of this study is to compare this with models. We have this very precise wind parameters, such as the velocity, the optical depths, the ionization parameter from the line ratios. And we also have a model for this warp disk precession, so we can say exactly where this wind is located when we are observing it. And so we can compare with 3D simulations of disk winds, assuming different wind launching mechanisms. Even after 2 decades of studies of disk winds in X-ray binaries, we still don't know what is actually launching them. Thermal driving or magnetic driving are both possibilities for these outflows. Now, in the meantime, actually this observation of Hercules X1 with CRISM is giving us also very interesting other results. This plot on the right is showing a zoom out of the figure that I showed us, the first one. And then there is this very interesting cyan, very broad emission line. This line is made of material that has velocities of larger than 0.1 speed of the light. This is very puzzling because we would not expect to get such a broad line in a system like an X-ray pulsar, where we know that the inner accretion disk is disrupted by the magnetic field. For Hercules X1, this should be at 1,000 kilometers. So the velocity should never reach anywhere close to 0.1 speed of the light. So actually with CRISM, we have confirmation that we have some kind of emission from within the inner accretion disk, somewhere along the magnetic field lines or in the accretion column, which is where the matter decelerates and shines in X-rays. And so this whole structure, this magnetosphere, is rotating every 1.2 seconds. So we would expect that this line, if it is made from the accretion column or the accretion column or the accretion curtain, it should be pulsating. And that's actually exactly what we see. So performing a pulse resolved analysis of this data set, here in red, I'm showing only the continuum variation. The x-axis here is the rotation axis of the neutrons, the rotation phase of the neutron star. And black is the best fitting parameters of the line. And you can see that the line is changing in all of its relevant parameters, the luminosity, the energy, and its width. As basically this whole structure is rotating and is projecting different solid angles towards us. Plus that we have relativistic light bending, we have relativistic beaming, and that's contributing to all of this variation. This is a very powerful way to study the properties of matter very close to the neutron star. This is an equivalent of basically relativistic line modeling black holes, which is typically used to determine black hole spins or inner accretion disk properties. So if we can develop a model to describe this line and how it varies, we can determine the orientation of the neutron star. And by studying this orientation over long periods of time, we can see how stable it is, or to say if there is a precession or any other kind of mechanism that would allow us to probe the interior of neutron stars, actually. So just to summarize, the warp precessing accretion disk of Hercules X1 is revealing for us the 3D structure of its disk wind. And the CRISM observation of Hercules X1 reveals this phenomenon in much greater detail. For the first time, we can see the wind kinematics and how they change with time. And besides the wind studies, we have this very exciting pulsating emission line, which we think is from very close to the neutron star and can tell us something about the accretion flow physics so close to the neutron star. Thank you.
Wonderful talk. Does anyone have any questions? We have a few minutes for questions. There's one over there, I think. Yeah.
Very interesting talk. So for like a black hole accretion disk with a relativistic iron line, we usually think of like the broad redshift of ring as telling us about like the location of the innermost stable circular orbit. What is the broad line telling you in this case, whereas you said that like the disk is truncated in the accretion column? Like what are you envisioning that to tell us?
Yeah, so that's the interesting part.
Yeah.
We have not only the time average information, we have information versus the rotation phase of the neutron star. So we don't know exactly where or how high it is originating from, but by combining all of this information with the rotation information, I think we should be able to constrain it. Like, these kind of motions are very well described. It is like free fall until the matter starts decelerating. So we should be able to say exactly how far up the column we are. And then from that, the orientation, because we have the energy of the line and the width of the line. So we have the Doppler shifts from both sides of the flow, actually.
Okay, cool. Any other questions? I think we have time for one quick one. Okay, if not, let's thank our speaker again. So we'll set up for a second. Put that on here.
Good. Thank you. Thank you. Okay, we've got a clicker.
Great. Yeah, so I don't think, yeah. Anyways, so the next speaker is going to be talking about white dwarfs. That'll be Tim Cunningham. So let's give him our attention.
Thank you. Thanks, Nick. Thank you to all the organizers for organizing a great symposium. Can you hear me okay here? Which microphone is it better? Are they both going? Or? Okay. Okay. Yeah, I'm Tim Cunningham. I'm just coming into the third year as a Hubble Fellow at the Center for Astrophysics. This is a list of many of the collaborators who contributed to some of the work I'll show you today. And as a quick update, I'm moving next year to the University of Warwick, where I will take the STFC Ernst Rutherford Fellowship, which comes with a position as assistant professor. I study white dwarfs, the end stage of life for most stars. And I study many different aspects of physics that white dwarfs can reveal, including convection and their diagnostic potential, studying the end stage of life for planetary systems. This is what I'm calling the exoplanetary HR diagram. This is every exoplanet host from the NASA Exoplanet Archive, so the host star of every exoplanet, including a few giant stars. Down here, this is every metal-polluted white dwarf, which now number in about at about 2,000. Also indicating a few known white dwarf planets, candidates, and transiting debris. So we really have a huge sample of these metal-polluted white dwarfs, and we know that the metals that are polluting these white dwarfs are coming from the tidal disruption and subsequent accretion of predominantly rocky exoplanetary material. White dwarfs are extremely compact, which is why I'm in this session here with Peter. We have something like the mass of the sun and the size of the Earth, and this high surface gravity leads to a rapid elemental sedimentation, yielding an onion-like structure in composition with a carbon-oxygen core, a helium shell on top of that, and a hydrogen shell on top of that. White dwarfs should just present pristine absorption lines, spectroscopically associated with either hydrogen or helium. But that idea was debunked even before we really knew what white dwarfs were. This here is the very first evidence of planetary material outside of the solar system. This is a spectroscopic plate that was taken by Van Manen. This is Van Manen 2 star, which it was thought at the time to be perhaps a K star, but it's now known that this is in fact a heavily metal polluted white dwarf. This is the same spectrum, the same star, different spectrum. And here you can see deep absorption lines associated with calcium, iron, magnesium. And this plate you can see in Pasadena at Carnegie. Since the discovery, retroactively, of Van Manen 2, the metals in Van Manen 2, there's been the detection of over 23 unique photospheric metals which can be linked to and which originate from the accretion of planetary debris. Among those are the elements essential for rock formation and for the formation of life as we know it. And I really like this exponential growth in the discovery date, and I'm very excited to see what metals lie ahead. So with this huge array of metals, you can do a lot because you can now start to pull out an inference about the parent body composition of the material that was disrupted and accreted onto the white dwarf. We have a sample of some 360,000 white dwarf candidates from Gaia, tens of thousands now spectroscopically confirmed, and this number is rising rapidly thanks to the multi-object spectroscopic surveys, DESI, SDSS, and Foremost, which is about to come online. So I'm interested in using this population to make inferences about the populations of planetary compositions, as well as studying processes in the white dwarf atmosphere. One thing that we can use the white dwarf population for is deriving initial to final mass relations. This was from a paper earlier this year, where we took a volume-limited sample within 40 parsec of 1,000 white dwarfs or so, and ran some population synthesis models to derive the latest update to the initial to final mass relation. This is mostly just a shameless plug for anyone who wants an IFMR for solar neighborhood stellar populations. The other thing that kept me busy since last time was a study of the mass distribution of polluted white dwarfs. In orange, you're seeing the non-polluted white dwarf distribution, and in purple, you're seeing the polluted white dwarf distribution from the same sample. So we identify a 3 sigma discrepancy between these two distributions, which is totally explainable by just there being no polluted white dwarfs with masses greater than 0.8 solar masses. I won't go into all of the details, but there are 2 explanations for this. One is that under some very simple episodic accretion model, more massive white dwarfs have faster sinking timescales. And so when you turn accretion off, you lose the ability to detect those metals much more rapidly. So in this population synthesis study, I showed that if all polluted white dwarfs actually have the same planetary properties in terms of planet formation and retention, then this result is fully explainable actually just by having some episodic accretion model. The other explanation is that intermediate mass stars of 2.5 solar masses or more just don't form as many planets or don't retain as much planetary material that can subsequently tidally disrupt and accrete onto the white dwarf. The way that the picture that we have in mind for how this works is that with the formation of the white dwarf, the mass loss from the progenitor is probably about 50%. In response to this reduction in gravitational central potential, the formerly somewhat stable planetary system now has orbits which have expanded in response to this mass loss. And this leads to a very nice environment with which we can gravitationally perturb smaller planetary bodies. If planetary bodies are perturbed onto sufficiently eccentric orbits, then this material will come within the Roche radius of the white dwarf and tidally disrupt. White dwarf's Roche radii are about 100 stellar radii, so we have a relatively large net within which we can catch planetary constituents. There's lots of evidence of these debris disks. They come in the form of stochastic transits of planetary material, double-peaked gas emission lines associated with calcium. This is calcium, the calcium triplet, 8500, and silicate emission. This is a Spitzer spectrum of G29-38. And so from studying the infrared, the mid-infrared emission, we can actually also back out the composition of the parent body that's being tidally disrupted, providing we have a mineralogical model of these silicate grains. But the key piece of evidence for accretion of planetary debris comes in the form of optical and UV absorption lines. Peter said R of 1,000 isn't very impressive in the optical, but actually it is pretty decent for white dwarfs. I mean, you can do a lot because the pressure in the photosphere broadens these lines so much. So with a measured metal abundance compared to, in this case, hydrogen, this is just an example. This is G29-38. We have calcium, magnesium, and silicon abundances, which we can couple with a diffusion timescale and derive a total accretion rate of metals, of the mass flux through the atmosphere, which we infer to be the accretion rate onto the star. This game is massively clouded by the physics of mixing in the white dwarf atmosphere. Crucially, it's important that we get the treatment of convection right, because large convection zones start to exist in the surface of white dwarfs, and this convection can delay the gravitational sedimentation. I study convection in these atmospheres using 3D radiation hydrodynamics, which, yes, because the 1D mixing length theory is known to produce a unphysical discontinuity at convective boundaries. There's no self-consistent solution for mixing where the Schwarzschild criterion is not satisfied. So to get the true hydrodynamic fluid properties of convection right, you need to turn to at least 2 dimensions. This is the emergent intensity from a cobalt simulation. I should have said I used the cobalt code. This is the emergent intensity for one of our simulations. And this, you see we get qualitatively get this granular convection, which is very much like what you would see in the sun. This is a solar observation, but I'll just note that the length scales here are very different. So the cobalt code solves the Euler equations in the presence of an external gravity field. We spend most of our time solving the radiative transfer, which is important for this optically thin convection. This is a snapshot. This is a 2D slice through some of my convective simulations. And I use this passive scaler to study and quantify the macroscopic diffusion coefficients due to convective overshoots. This leads to a predicted increase in the accretion rate. So this here is effective temperature, and this is inferred accretion rate, and these are corrections due to overshoot. So I've been targeting this specific guy here, G29-38, to see if we can measure the accretion rate and find independently the instantaneous accretion rate onto this system. So this was a discovery that was made in 2020. We, for the first time, measured an X-ray luminosity from a metal-polluted white dwarf. Sorry, I'm skipping over a lot of slides here, but this is the X-ray accretion rate that we measured with Chandra's ACIS detector. I just want to point out that the fact that this agrees to even within an order of magnitude was kind of amazing to us, because this is a totally different accretion model. So in the green line here, this is taking calcium, magnesium, silicon abundances and coupling them with diffusion timescales in the white dwarf atmosphere. Whereas this blue band here is measuring an X-ray accretion rate. So the blue we really think is the instantaneous accretion rates, whereas the green line here is time averaged over the diffusion timescale of the white dwarf, which is on the order of years. I just want to advertise that I now have some preliminary results from an ongoing Chandra HRC monitoring program. This is certainly not as impressive as Peter's X-ray light curves, but I think this is the lowest X-ray luminosity potentially measured outside of the solar system. There's a luminosity of 6 × 10⁻25 ergs per second. So this is the very first long-term constraint on the instantaneous accretion rate for any white dwarf accreting planetary debris. The fact that we've not detected variability is, I think, great news for the community of metal-polluted people studying metal-polluted white dwarfs. It says that perhaps accretion rates are not expected to be variable. And I think I will just leave it somewhere. I think I will leave it there. Thank you.
Great. Does anyone have any questions?
Hi. This is fascinating that the white dwarfs can be polluted by planetary material. I actually didn't know that before. But I was curious if you thought of the possibility that it could be polluted also by like a companion white dwarf that may have exploded previously, or maybe the rates aren't high enough for that. And then separately, like, could this pollution from the planetary sources be a source of like higher metallicity for white dwarfs before they explode?
Yeah, good question. So I think on the accretion from a companion, we find that about 50% of white dwarfs show metal pollution from planetary debris. So just the occurrence rate of finding these metals kind of implies that wouldn't be the predominant mechanism. You also need the accretion to be ongoing. So because the metals will sink extremely quickly from the atmosphere of white dwarfs, if it's not convective on the timescale of days. So depending on the temperature of the white dwarf, merely detecting the metals is really telling you these are being constantly accreted. So you need some kind of ongoing reservoir. So generally, generally if there's ongoing accretion, you might expect to find some infrared excess. That's not true in all cases, but yeah, certainly in many of these cases we see infrared excess from dusty debris disks. In the case of a companion reservoir, you should probably expect to see some additional signatures there. Yeah, did I answer your question? Yeah.
Great, let's thank Tim again. So I believe next we have the earlier career panel, is that right? Okay, yeah, cool. Moment for that.
Well, I put my mic.